Folks, welcome back. This is page 3. We are now going to look and use properties of similar triangles again, and maybe learn a little bit more about trigonometry. So let's take a look at the picture we have here. We're going to let point P, be located at x comma y, and that is on the unit circle. And it also lies on the terminal side of theta. Remember, terminal side of theta means it's this side of theta, not this side. We call that the initial side, and then the top piece, the terminal side. So I'm going to go ahead and erase that. I don't need those. Okay, so use what we know about geometry to determine the y-coordinate of point Q and the length OQ. So these are the two things we have to determine. We have to determine this length right here and this length right here. So that's what we're going to try and do right now. What I'm going to do is I'm going to just try and sketch this figure off to the right so we can kind of annotate on there. So let me do my best to sketch this figure. Okay, so this is a right angle, this is a right angle. This length right here is x. This length right here is 1. This length right here is also 1 unit. And this length is y. So we're asked to find this length here. I'm going to go ahead and label that. I don't know what letter to use, so let's just use lowercase a. And then we're also asked to find this length here, and just for fun, let's call that b. So b is this entire length right here. Well, let's look at a first. And what I want to do is first of all, theta is right here. So I have a pair of similar triangles. This triangle is similar to this triangle by angle-angle similarity. So I can start comparing some side length ratios and set up proportions. Let's do that with the triangle, the smaller triangle, and then the bigger triangle. So I'm going to say in the smaller triangle, I have the adjacent leg to theta divided by the opposite leg to theta. That's x over y. If I do the same thing in the bigger triangle, the adjacent leg is 1 and the opposite leg is a. So if I solve this for a, I get a equals, let's see, doing a little bit of manipulating there, y over x. So I have a equals y over x. Well, I already know that y is equal to the sine of theta, and x is equal to the cosine of theta, based on our unit circle work that we've done before. So what that really means is that a is equal to the tangent of theta. So you want a physical representation of what the tangent of theta is? It's this length right here. Okay, that's geometrically what the tangent of theta is. It's that length. Okay, let's now, that I find fascinating, by the way. Let's now jump into and look at b. So I'm going to do something similar with b. Again, I'm going to compare sides in triangles. Let's take a look at the small triangle first. I have the adjacent leg to theta divided by the hypotenuse. That's x over 1. Now in the larger triangle, the adjacent leg is 1, and the hypotenuse is what we're calling b. So if I go ahead and solve for b here, I have b equals 1 over x. Well, x is cosine of theta, so this becomes 1 over cosine of theta. And if I use that new reciprocal identity we just learned, that means this is equal to secant of theta. Okay, so if you want to know what the secant of theta is, a geometric representation of that is this length right here. Okay, that's fascinating to me, folks. And let's take a look. Let's see if we can do anything else with this new information. So we've got this triangle here. and we've got theta, and then we've got the length of the unit circle radius as 1, and we've said that this is equal to tangent of theta over here, and the hypotenuse is equal to secant of theta. Well, I don't know about you, but anytime I have a right triangle, I want to see if I can apply the Pythagorean theorem. Well, I sure can here. I've got leg squared plus other leg squared is equal to hypotenuse squared. And folks, pat yourself on the back. You have another Pythagorean trig identity. Okay, we already have sine squared plus cosine squared equals 1. And now we have a new one. 1 plus tan squared equals secant squared theta. Okay, there is one other Pythagorean trig identity. I will not derive it for you like I just did this one. I'll just write it out for you. It's 1 plus cotan squared of theta is equal to cosecant squared of theta. Okay, and as I mentioned already, these are called identities, which means they are true based on true for all values of the variable unless I have any restrictions. So this is for the one on the left, 1 plus tan squared equals secant squared. That's true for all values of theta except where the tangent of theta is undefined, except where the secant of theta is undefined. Same is true for the Pythagorean trig identity on the right. Those are true as long as you're not dividing by 0, basically. Okay. Speaking of identities, this whole lesson was supposed to be about trig identities. So let's talk about what it means to verify an identity. Okay, first of all, I'm going to tell you about strategies, not procedures. So it says here we're talking strategies. There is no procedure to verify a trig identity. What I mean by that is I can't tell you that you will approach every single one the same way. What I can do is give you some strategies, okay, of some things to look for and some things to try. However, there is one rule I want to make sure that I state, and this is kind of one of those things that this is very picky from a mathematical standpoint. You must only work on one side of the equation. So what you're used to doing as an algebra student is doing things to both sides of the equation, work on the left and the right by doing, maybe adding 5 to both sides of the equation or taking the square root of both sides. When you're verifying a trig identity, you're not allowed to do that. You got to pick one side and work on it and make it try to make it look like the other side. Okay, so you pick one side and you try to make it look like the other, and if you do, then you've verified that identity is true. Okay, so here we'll just tick through some of my bullet points here. Try working on the more complicated side of the identity first. Try to make it look like the simpler side. That's just a strategy, not something that you have to do. Use reciprocal and quotient identities to write functions on one side of the identity in terms of functions on the other side. So I try to take tangent and rewrite it as sine over cosine. I try to take secant and write it as 1 over cosine, those types of things. If you get a rational expression that doesn't have the same denominator, make sure you want to add them, get a common denominator first. Use Pythagorean trig identities wherever you can. If you find yourself stuck working with one identity on one side, then try starting over and look at the other side and see if you can make instead of making the left look like the right, see if you can make the right look like the left. Okay, so what the heck does it mean to verify an identity? Let's look at an example here. So this is a pretty straightforward one. We've got the tangent of theta equals sine of theta times secant of theta. So to me, it looks like this is the more complicated side. So that's what I'm going to start with. So I'm just going to rewrite that. Sine theta times secant theta. And I know sine theta is good to have. I can write that as sine theta over 1. The secant theta, well, that's the reciprocal identity with cosine. So the secant theta is 1 over cosine theta. And then if I multiply these two fractions, which I can do, I just have sine theta times 1 in the numerator and 1 times cosine theta in the denominator. And once you look at that, sine theta over cosine theta, that's our definition for tan theta. So what I would say right now, folks, verified. That's green check verified. Okay, that's a quick example. I've got 3 more on the next page, so let's jump over there and take a look at those.